Okay, we're going to talk today about system approach on the topic that basically uh, covers many aspects of discipline of study. But of course, because this is the lectures in engineering, especially in mechatronic or IT or industrial engineering also, we'll cover it from that point of view. Let me just share the file. Yeah. So we'll talk about system approach. Yeah. What is actually system approach? It is actually the definition. It was given by Ludwig von Bertalanffy in 1968. It was originally called it was originally called the general system theory. Yeah, but of course it becomes a system approach. It's an old concept actually, but this approach stands on the assumption that breaking down of a complex concept into simple, easy to understand units that helps in better understanding of the complexity. Yeah. So I put down there number one and two, actually the reference for where I took it from. So what makes this Bertalanffy's approach to system analysis is important because of its applicability to so many different fields. And of course, it wasn't designed for engineering in the first place. But of course, in engineering, we are applying it, especially there are quite a few. But the one thing that I know that I took the course is in the Siemens mechatronic system approach. Yeah. Actually, it's a certification exam that my institution and I have the the ability to conduct exam for Siemens certification for that. So it is called a system approach. Yeah. So system approach is based on the generalization that everything is interrelated and interdependent. So when you talk about a car, yeah, every part of it, we can say that maybe some people will see the wheels, the steering wheel are more important than the machine or the valve, but actually all of them are interrelated and interdependent. So a system is composed of related and dependent elements, which when in interaction forms a unitary whole. Yeah, a system is simply an assemblage or combination of things or parts forming a complex whole. Yeah, so that is actually the definition of system approach. So I want to look at it, cover it a bit in mechatronics or in engineering. What system approach is defined there or is implemented or applied in engineering. So, for example, traditional approach as compared to system approach is that when we study, for example, in engineering, here is electrical engineering. We usually study in the beginning the electricity, the quantities, the units. Yeah, that's how also I used to teach. Of course, I'm still teaching in similar way in terms of the parts. Yeah, I'm still teaching that, but now we are looking from the system approach first and then going down to the nitty gritty, but I will talk about it more. So in traditional approach, we study the electricity quantities, units, the engineering notation and metric prefixes and all that, the units. And then what else? Voltage, we study what is voltage, what is current, resistance, Ohm's law, energy and power, and Kirchhoff voltage law, Kirchhoff's current law, and then Ohm's law, and what is the circuit in series and parallel. Yeah, that's how we study in engineering, especially electrical engineering or mechatronical engineering. So that's how we studied. It doesn't mean that we don't study anymore such as this, but the approach is different. So the fundamental is actually the explanation of the voltage, current, resistance, and laws, Ohm's law, Kirchhoff law, and other laws, and circuit law, and all that. And then after that, probably we go to further. the principles of electrical components, the theory of measurement, how to calculate them, how to measure them. And then probably we go to the lab exercises, we go to the laboratory, and then to actually experiment something. And then, of course, the exercise is to exercise with single components. And then we got these resistors, we got these inductors, and then we measure what is the current flowing through it, and so on and so on, which is okay, but mostly is no whole system exercise. Yeah. So we are trying to, I wouldn't say revolutionize, it sounds so big, but we want to revise the way we approach the teaching or the lecturing methodology. So the traditional approach, of course, like I said before, it is building the theoretical fundamental first. What is current, what is voltage, and then what it is being built to support what. And then by this, then what are the principles on top of it. And then we go to exercises, and then finally, we go to the system, mechatronical system or engineering system or IT system, yeah, I guess, yeah. So what actually is doing, what actually we are doing in traditional approach is that we are coming from the bottom, not from the top, the system. Yeah. So when we go to the system approach, it's a bit different in the way that we start with the system approach from the system first. Yeah, I think it is quite obvious. The thing that I'm talking about system. So everybody knows the system is the whole thing. Yeah. And then we go down. What are the modules in that system? For example, in a car, what are the modules? The steering modules, the ignition modules, the transmission modules, and all that. Yeah. And then from that module, what do we have actually in mechatronic system? We have electrical subsystem, we have mechanical subsystem, we have control subsystem. And then from that also, we have this electrical, we have this ultrasonic sensors, we have these solenoid actuators. And then in mechanical, what do we have? We have a clutch, yeah, clutch like in a car, and then belt drive, yeah, that spins something. And then how do we control it? With digital logic, with programming techniques, and all, whatever it may be. So the approach is from the top. So we want to know what actually this mechatronical system is doing, or is designed for what. And then to set the target or to achieve the target, then what are these modules doing, and then these modules is supported with what components in it. And then each components, what are the characteristics, what are the limitation, what are the source of error if it doesn't work, things like that. So system approach is actually looking at from top to bottom. Yeah. So as we learn the theory from the system, after, it doesn't mean that we don't learn the theory from the system. Yeah. The theory at the bottom we will learn, but not before we learn about the system as a whole. That is the system approach. Yeah. So let me look at it from the mechatronic system, because this is what we applied. Of course, this can be applied in other systems also, not just in mechatronic. It can be in electrical, mechanical, or automotive, even in IT. In IT, we think that it is just about programming, but even in the program, you are wanting to see the system, what it is doing, and then you go to every module, right? Every module has to work very well to combine, to be connected. Even when you have a SCADA system, a bigger system that is connecting a subsystem together, then you need to understand the system as a whole, so that each subsystem will work with each other, with other subsystems, to support the target or the aim of the whole system. So let's look at a mechatronic system here, system approach learning loop. So if you have for example, let me make my laser here. if this is a mechatronic system, then this is an example picture. If you can see the picture here, is some people looking at some modular processing system. This could be a stations. Yeah, it comprises of many stations. One station is for sorting, probably. One station is for testing, and the other for assembling, and then whatever. Yeah, and then each of them is connected to each other, and then they are controlled by the bigger system. And we usually call it maybe each its station is run by a PLC, and this PLC is connected to another PLC, and so on and so on. So let's look at this system. So we are looking at the big system, and then we separate them, or I would say we split them into modules, right? Modules that works interconnected between one another, and then this module, each one of them, we go down. So we go down here. So we go from the top, we go from the system analysis. So from each module, we know that each module is doing what? Like I said before, probably it is a sorting station, assembling station, and then checking station, things like that. And that module, of course, we want to know what are the application of components in that system. If system is for sorting, then they must have some kind of a mechanism of checking. Maybe there are some sensors, maybe there are some actuators to reject or to accept. So we know the characteristic or design of the function in the system. Yeah. So when we go to probably sensors to check so that we can differentiate the product or the components, then of course the sensor have some physical principles in there, right? Characteristic, limits and values, and source of errors if it doesn't work. Yeah. And then if it doesn't work, we know, then we can check what are the causes of the malfunction in the system. Yeah. So from here, we go to the next one. So this is a comprehensive system skills. So from here, when we know the physical quantities, principles, characteristic of that components, maybe this is talking about the resistor that we study in the traditional approach. We studied from that already. But from the system approach, we study the system, and then we go to modules, we go to the application of the components, go to the characteristic of the components, and maybe it's talking about the resistor, talking about the capacitor, talking about the solenoids, talking about the sensors. Then we study all of that, and then if it doesn't work, then we can understand what causes the malfunction. It could be also the connection to it. And from that, we can, of course, trace the signal flow measurement. Then we can do the troubleshooting strategies in that. So we can understand the whole system. System approach is actually helping us to save time in the onboarding knowledge. You know, when we are talking about what happened to my capacitor, what really happened to my system, yeah. So it's like you have to study the little thing first, and then you have to study the bigger thing, and then come back to the little thing again. So it's rather, let's go to the system approach. For example, this is the way I always look at it when I tell students, especially about transistor, for example. Yeah, transistors those days, like 50 years ago, 60 years ago, is actually made of a capsule type of container, and is very big. That's why computer those days can be as big as the size of the room, yeah, of a school room. But now it is very small, micrometer. Sometimes micrometers technology that we call it now, even going to nanotechnology. Even your computer, our laptop, it contains probably billions or trillions numbers of transistor in it. Yeah. So when I said to students when I'm teaching that, and I said, look at these transistors. It is talking about switching, right? Zero, on and off, on and off. Isn't that what computer is all about? 1010. So if you can make a very big combination of 1010, You can make some words, some letters, some numbers, or even you can make some a configuration of pixel. That is what we can see in our screen. Is talking about combination of all this, So when something doesn't work, one thing or another doesn't work, probably we can trace it down to that components that doesn't work. It's not just about understanding what a transistor will look like, what is this, as you know it, there is the base, emitter, collector section, and all that, things like that. So we go from the bigger approach, which is the system approach, and then we go down, just like this, go down. Okay, let me just continue, right? So this is just one example of system approach. This is a gear sorting line. When you look at it, we're not going to discuss this over in detail. I just want to be in detail, but I just want to show you. But when we see this, the first question that we want to know as a system approach mechanism is that, what does this do? Yeah, what does this gear sorting line do? What does it sort? Oh, it sorts some components, some gear, definitely, because the name says so. So what does it do? And then how does it work? So it comes from here, and then it will stop here, will be checked here, will be rotated there, and then will be pushed, and then assembled here, and all that. And then the next question is, how is the system broken into modules? That is important. So we want to know how this system is broken up into modules. Like I said before, maybe this module is about what? Like cars. A big system is car. The point of having a car is so that you can be using it, transporting you to one point to another. That is the point. The vehicle, the purpose of that. So when we want to analyze that car, then we want to see if it doesn't work. Then when we have it in modules, broken up into modules, we know where the problems come from. For example, it doesn't ignite. When you try to ignite to start the car, it doesn't start. You can check what is the connection, the module, the battery modules. It could be the battery modules. But when you check the battery, oh, this is working. Or maybe what? Maybe it's the ignition, maybe the combustion, maybe whatever it may be. If it is electric vehicle, I don't know, maybe the motor doesn't work, things like that. Maybe because you're using some battery that and then you have the inverter to start the motor, because it's a three-phase, because it is you have to transport it from DC to AC, things like that. Maybe the inverter. So when it is modularized, where to check. Yeah, and we continue. So this is again a smaller part. Yeah, you see the bigger part. If you can see here, this is the gear still sorting line, but this is in the module of gear supply module. So the gear supply module. Then what does the module do? So you ask the same question. You see the bigger system. What does the system do now? What does the module do? And after that, how does the module work? Again, the same thing. What happens in the module? How does it work? So that's how to actually ask the question so that we know it. Yeah. So if you look at this, let me just show you the parts. Yeah, in this module, which is there's a storage pallet. Yeah, storage pallet. Pallets being stored in here, and then there is this DC motor. Yeah, that drive some part in here, and then chute is where this part is moving down here and will be stopped by a stopper driven by solenoid here. Yeah, solenoid there. Yeah, solenoid will drive the stopper. Yeah, after it is going down, after the components going down the chute, and then the gate when it is open or closed, so that the components will be allowed to go through some chamber. Yeah, some collector here. Pneumatic cylinder. This is actually for being extended and then push something to the other. So proximity sensors, he had so many proximity sensors here. What does the proximity sensors do? Yeah, it is sensing proximity in the proximity in the distance and near distance. So when it is going near a position, the proximity sensor will sense it and then will inform the brain, the PLC, the computer, the PC, that the component is there so that we can make another decision to move. So these are the components. And what else? These are the gears. Yeah, gear presence sensor. So when the component, the gear goes down, and the sensor will sense it and then will tell the brain, whatever the brain is, can be PLC, microcontroller, or even PC. Yeah, and then we'll do accordingly the next action after knowing that. Yeah, so this is actually transported from the right side here. Yeah, this is I picked up from my lessons in Siemens, and this is right on the board how the information flow, how the material flow moving from one point to another, and how the energy flow in here. Yeah, PLC having energy going to electrical energy or power energy going to the component. So this is I'm not going to discuss, of course, in detail. I'm just going to show you how it works when we analyze a mechatronical system. So this is actually the system approach. Before we go to each, so after that, after the system is modularized, in module there is some characteristic, something that we can see a bit more detail. Then we go to select a component. Now let me choose a solenoid. Yeah, solenoid, it is where we stop. This is the chute. The chute is where the gear component will go down and then will be stopped by this solenoid stopper. Yeah, and let's look at the component. This is when we want to actually study the solenoid. How does it work? Yeah, so we know from the system approach. Yeah, solenoid here. Okay, so what does the component do in this module? Again, we ask the same question. How does it work? What does it do? What does it contribute to this module? Okay, so let's see the characteristic of the design or function in the system of this solenoid. Yeah, this is Y1 solenoid. So you can see here there is the there is this extended part of the solenoid that stop this gear component, and this is the sensor. Let me just go open all this explanation. This is the chute before. This is the part presence sensor. So this is the gear sensor, yeah, proximity sensors, and there's also sensor here in the module here. There's some carriage where to collect it after being accepted by this extended solenoid. Yeah, this is solenoid itself. Okay, so this is the gate. The gate is being closed or opened by this solenoid. So that is the purpose of the solenoid. So actually, when the parts coming here, yeah, then the part sensor will check it. Is it the right gear? Is it the right component? Then if it is the right component, then it will be accepted. Or for example, the carriage will be defined later. We don't know. Maybe the carriage is also classified also. For example, this kind of carriage will only accept a metal gear, or another carriage will only accept a plastic gear, for example. So the importance of this part presence sensor is to differentiate what kind of gear is this. Is it correct or not? So then the information will be fed into the brain, and the brain will do action whether to extend or retract this solenoid action. Yeah, so that's the characteristic and function of that. So we can understand it, and then we go now. Okay, this is the part. This is the gate also, and look at this one there, and then it's being being accepted, and then it goes down there. Yeah, so that's the purpose. So then we go to the physical principles of the solenoid. What is the principle of solenoid? Solenoid is it having a plunger there. And inside, you can see here, there is a stationary core. This is a ferromagnetic core. And there is also a sliding core. And if you can see here, this one, this color here is actually a winding, yeah, a winding. This winding will be carried, will be fed with current going through it. So when current going through the here, then it will be energize or magnetize this core, this two core. Yeah. So that's how it works. So if you see the spring here, without any current going in, let's say it is no current in, so it is the normal position, then this is extended. Yeah, this plunger is extended. So when the current is, I will show you later a bit more picture. When the current is going through this solenoid, then this one will energize and will attract this plunger in. Yeah, so the plunger will move in. So that's when it is being retracted from here. So it is like being retracted into it, because there is a pulling mechanism by this core, pulling and pulling each other. Yeah, and then it will. So when the current is cut off, then the spring will push it back to its original or normal position. Yeah. So then we know the function. Yeah, the function. We know it is needed to stop something or to let something go, passing it. Yeah. So this is the core, the physical principles of it, and this is the picture of it, and the other one, this is just type. Yeah. So we are keeping the module as the context in the context also. So look at this. Yeah. So when the current is flowing, what are the underlying physical principles of the components? So when the current flowing, you get here, current going in here through the coil. So this core is somehow being energized, so it becomes magnetized north and south. This one also north and south, because they are basically going through the same direction of winding. So if they are become magnetized, the ferromagnetic materials, then they will be having the same direction of magnetic field, I would say. Yeah. So this one is north and south. This one also north and south. You know that the opposite polarity will attract each other. So look at this. So they will be attracted to each other. So this one will be pushed in. Direction is to this direction. And then when the current is cut off, it will go back to this original or normal position. So the idea of this is voltage given and produce current and produce magnetic field, and then the magnetic field will create a magnetic force, and then the movement of that. So that's the physical principles. Sometimes we think that it's too long of an explanation, that just want to know this part. Yes, but then when we want to study the whole system, then we have to remind ourselves about this context again. And it is better to actually going to the big system, the whole system, and then going down as like a bridge, a bridge, what it is for, the modules, and then the characteristic, and then go to the principles of it. And finally, we can discuss the components by itself, the principles behind it, and so on. And I think it will stick better, because we know the application, the implementation of it. So after that, then you can go finding your own way to actually see more of the components. You can just Google it. Yeah, just put here Googling. You can learn how to use the data sheets, the internet, training materials, and books even, just to see more of it. You can see the graphs here of force against stroke in millimeters and so on of it. And then you can even find the types of them, even with a different brand and so that. So Google is actually or other source, you can use it to even go deeper on that. Yeah, but when you know already the modules, the modules that this component support, then you know, with a bigger, somehow our brain is also connected in such a way, you know, it's connected, wired actually to something which is talking about the purpose, the usage, the bigger picture, and it helps us to understand it and to remember it better. Yeah. Okay, so the characteristic, for example, you go down from I'm going to be quick on this. Solenoid coil type, you can check the AC or DC type, the power consumption, how many watt, how many voltage, and then voltage specification. Is it 24 DC or AC? And then what is the voltage range that it can handle, duty cycle 100%. And then what about the solenoid life cycles? Is it 50, this is here 50,000 cycles, so after doing it for 50,000 times, probably it should be probably it should be replaced, you know, like that. And what is the operation, push-pull engagement, and so on. So you can discuss it more and more. Yeah. And then source of error, of course. Let us talk source of errors for this. So we are looking at it from system approach, but we also look at it from all aspects of that components. What are the limitation of the component, or what are the limitation of this component? What are the possible causes of malfunction in that component? If it doesn't work, what happened? Yeah, and can be broken wire. Yeah, because you know the components, it connected with a wire for a power or energy supply, and then the coil can be shorted. Maybe the cabling is broken, and isolator is broken, and they get sorted, or plunger not movable, can be mechanical problem, or can be electrical problem, can be spring problem, spring is broken, I don't know, broken spring, I just mentioned it just now, and so on and so on. Yeah, so let's look at it, learning steps. Yeah, so we go back after we know the problems, and we go to learning steps, how to identify the malfunction. So it is not just, you know, putting your hands on the forehead. So what happened to this? What happened to this? But you can identify the malfunction in that, and then we can do other techniques, which is how to measure it. You know, when you study capacitor, you study resistors, you study that, and then you want to measure actually what are the value. Is there any current flowing through that? Yeah. And you can simulate, of course. So let's look at the learning step, developing strategies to find out the malfunction in the system, not only in the component. So the component is in the system, but the system, it doesn't work, can be in the component, but we can see probably the interconnection between that component and another component. Short and clear description of the problem. Is the gear present? Yeah. Is the gear present? If not, then are the present gears detected? Or probably it is if the gear present, probably the sensor the problem. Does the sensor send a signal to the PLC? So does it? We check in the PLC. Yeah? Is the voltage applied to the PLC output? So the PLC actually have any supply to that? Or is voltage applied to the solenoid? And the solenoid probably doesn't work. You know, when we see the problem that solenoid doesn't work, what happened? Oh, there is no gear. Yeah, of course, there's no gear present, so it won't work. It won't lift up. It won't open the gate like that. But the gear is there, so probably the problem with the sensor. Oh, sensor is okay. Then probably it doesn't set the signal going to the PLC is stopped. Cable is broken and so on. Is there any voltage? Yeah. Or probably everything is there, but we send the signal to the solenoid, but it doesn't reach the solenoid. Could be the case. Yeah. So situation is this. Let's just make a troubleshooting example. Gear is present at the gate, but the gate does not open. What happened? Yeah. So the question is this: is the present gear detected by the sensor? So we check. Sensor is triggered. LED of the sensor is on. So in here, the LED is on. You can look at it here. LED is on. Okay. So gear is there, but the sensor is on. And then, okay. Does the sensor send signal to the PLC? Because it must send signal to the PLC. Yes, status indicator is on in the PLC here. It's on. Okay. So it's okay, sensor is okay, and then the signal is received in the PLC. And the next thing, is the PLC output set to open the gate? So is the PLC output tell the solenoid to open the gate? So let's check. Oh, the status indicator here is on. So signal is on the way to the solenoid. Yeah. But is voltage applied to the solenoid? We check the voltage. Is 0. From A1, yeah, here A1, A2 is 0 voltage. So now, okay, should be 24 volt. Then we know the problem is in here. Yeah. So check the cable between PLC output and solenoid. So probably that is the problem. Yeah. So that is the troubleshooting example that we can see. Yeah. So and then after that we go to the system again and check where does the component appear as well in the entire system. We check again. If with the same solenoid, we check. Yeah. If it doesn't work, we know what to do. Yeah. So it's not just studying the component, but studying the component within the system. But of course, we must understand first what is the system for. Yeah. There's a big what is its function or purpose at each location in machine, and then we copy the same checking like before. Yeah. Oh, just the test question before we finish about this system approach. The question is this: which of the following statement about the testing solenoid coil is correct? Yeah. A, when a two answers here are correct. When a solenoid coil is checked, a reading of infinity on the ohm meter indicates a partial short. Yeah. When infinity ohm meter, it means that actually is an open connection. Yeah. Not a partial short or a short. Yeah. Because there is no is an open, so that's why it is yeah, infinity, a very big resistance checking. B, so A is not. Yeah. A, an ohmmeter check of a good solenoid coil will indicate the value of inductance. Well, ohmmeter is checking ohm, not checking inductance. Yeah. So it's not correct. C, if there is an open, an ohmmeter will indicate infinite resistance. Yeah, I just mentioned it when we are answering A. So C is correct. Yeah. D, if the solenoid coil is good, the ohmmeter will show the winding resistance. Yeah, of course. Ohmmeter, we call it ohmmeter. E, if all windings are completely shorted, the solenoid coil will have infinite short resistance. Of course, this is wrong. This is the same thing as A and C. Yeah. So the answer is C and D. So this is how to actually can apply after studying that. Then we and then checking using measurement also. Then we find out on this. Okay, so come back to system approach learning loop. So we start from a bigger system and then going to each modules, if we can modularize them, and then go to the application of each component and then the characteristic and design, and then go to the basic principle of it. So then we can see if there are some problems, malfunction in the system, then we can check the characteristic and the sources of error, and then we can trace where the signal flow and then find the troubleshooting strategies in that. This also applies to any other subjects, not just in mechatronics. Even in life, yeah, we see when something in an organization, even something that doesn't work very well, maybe we modularize it based on the business process, of course. Yeah, so that's it for a system approach. We'll discuss something else later. Thank you.